Hello students. So in the last video, what did we do? We showed that if we had linear maps, we could add them and we still get linear maps. And if we have a linear map, we can scalar multiply and that will also give me a linear map. So let's think about that. One thing I could do is I could take the collection of all linear maps. So let's do that. Let's let L of V comma W be the collection of linear maps from V to W. So let's think about that. Now, I have these linear maps from V to W, and I can add them, and I can scalar multiply them, and they give me new linear maps. So let's just think for a moment. You have a place where you can add things and you can scalar multiply. What's that called? If it meets the correct rules, which it might, what's it called? It's called a vector space. If it meets all the rules that we would want. So, this is a little tricky. Think about it. We have a vector space V. We have another vector space W. I'm taking the collection of all linear maps from V to W. This in itself might be a vector space. And it turns out it is a vector space. So we get a vector space of maps from this one vector space to this other vector space. Okay, so how could we show something like this? Well, the zero map is going to be linear. If we want, we could call it Z of V instead of, trying to do some weird O thing, right? But let's just say Z of V equals 0 for all V. Or I'll write that out. For all V. Okay, this is going to be a linear map because Z satisfies Z of V plus W equals Z of V plus Z of W, and it also satisfies Z of lambda V equals lambda Z of V. Why does it satisfy these things? Well, because 0 equals 0 plus 0, and 0 equals lambda times 0, the 0 vector in this new space that we're constructing, LVW. Okay? So we have a zero transformation. But if I take the zero transformation, and I add it to any transformation, what do I get? I'm going to get that transformation back. Why is that? Well, it's going to be because Z plus T of V is a short proof of that fact. I'm not writing proof out each time, but these are proofs. Well, Z of V is 0, so this is the 0 vector plus T of V, which is just T of V over there. So, the 0 map is linear, and if I add that 0 map to any other transformation, well, that 0 map sends that transformation to itself. Now, you might say, okay, you only did that on the left. Yeah, but I'm going to show commutativity now. If I have T plus U of V, that's equal to U plus T of V. And why is that? Well, that's because T plus U of V is equal to T of V plus U of V. But this addition here, where does that take place? That takes place in the vector space W. But W is an abelian group under addition. It satisfies those addition axioms, so that equals this, which is equal to U plus T of V. So we have commutativity. So we have commutativity and we have an identity. We also have associativity. TU, I don't want to use V for my third map. S. Not the most interesting one to show. Not super long, not much long, but a little longer than this and not very interesting. Why don't you guys try and see if you can do that one? But what else would need to be shown? Well, we have associativity, we have commutativity, we have an identity. What do we need? We need inverses. So for any map T, I want a new map that takes me back to the 0 map. So how would I do that? Well, for any T, which is linear from V to W, I can find this is just going to be that map. So, well, I wrote the minus on the wrong side there. Okay, so what this is saying is that the inverse of the map TV, very sorry about that, that's a bad mistake, but I saw it right away. The inverse of the map T of V, otherwise this would not mean the same thing, the inverse of the map T of V is equal to, well, what do we know? We can always take lambda t for any t, right? We know that. It's going to be the map minus 1t of V. And to show that, well, t plus minus 1 of t of V is equal to what? Well, by the definition of the sums of maps and, well, let's split this up. T of V plus minus 1t of V. So what's that going to be equal to? Well, it equals T of V plus, by the very definition of lambda t, minus 1 T of V, where this is a multiple of the value T of V. So what is this equal to? Well, this is just T of V minus T of V, which is 0, which is equal to Z of V, regardless of what V is, because Z of V sends everything to 0. So what did we just show? Well, we showed that this map under addition is a abelian group. It satisfies the 4 axioms. There are 4 more axioms involving scalars, right? We have 2 distributive laws, and we have a compatibility rule, and we have our identity rule, but those are not much harder to show, so I'm going to leave those. But what did we get? We got this weird thing where we took a vector space and another vector space, and then we considered the linear maps between them, and that in itself is a new vector space. And this is a very important vector space, the set of linear maps from one vector space to another. So this is definitely something that's going to come up a lot in the future.